Hello, everyone. It looks like it's time to get started. Welcome to our manufacturing webinar devoted to the topic Injection Molded Parts, Concept to Production. I'm your host, Lacey Cantrell, Marketing Content Strategist for MW Components. For those of you who are not familiar with us, MW Components manufactures stock, standard, and custom parts for various industries and applications. I'm joined today by William Johnson, our subject matter expert and the presenter for the duration of this event. William is our in-house plastics manufacturing expert. He has a Master of Science in Plastics Engineering from the University of Massachusetts Lowell. While at UMass Lowell, he taught graduate level labs for the Plastics Engineering Department. He has worked with MW Components as a process engineer and has recently transitioned to MW Components Sales Division. In his role as a process engineer, he often supported projects which require demanding tolerances, and he has experience assisting with the development of unique product designs and processes for various industries, including medical, electrical, and industrial. Will is going to present very shortly, but before we begin, I'd like to let you know the structure of today's event. This webinar is expected to last around 45 minutes to an hour. First, our presenter will go over the content, and once that's complete, there will be time for a short question and answer session. Then we will go into wrap up and closing. As you think of questions during the presentation, feel free to add them in the Q&A section. You can access this by clicking on the Q&A icon at the bottom of the screen and typing your question into the box provided. Depending on the nature of your question, we will either respond immediately or questions will be addressed at the end of the call during the designated Q&A portion. I will now let Will begin.
Thank you, Lacey. So I'm going to get right into it. We're going to start with a general overview of the process so that we know what factors we're dealing with as we get into it and start looking at my example part. So my objective here is going to be to educate on the process of injection molding, its benefits, and how to design for it. We're going to be going over a lot of rules of thumb and kind of how they are backed up by the science in injection molding. So what is injection molding and how does it work? So injection molding is really a single additive process that produces the parts. It is a one-stop shop, as it were. And how it works is generally 5 steps. First is the plasticizing. Plastic pellets are heated through shear and conduction, while you'll see in the GIF underneath there, the screw turns. That turning is causing friction on the sides of the barrel and between the screw, shearing the plastic. And along that entire barrel are heater bands, usually at temperatures between 300 to even 800 degrees Fahrenheit. One of the interesting things during plasticization is that the shear is really what's doing a lot of the heavy lifting when it comes to melting down the polymer pellets, because that friction is so extreme that it really breaks them down and increases the amount of energy in the system. And so plasticization, when it comes to injection molding, is one of the most important steps. Without a homogeneous melt, without the melt being the same all the way through, you're going to have a lot of issues with the finished product. So moving on, there's injection, step 2. The screw is forced forward, pushing the molten plastic through the nozzle and into the mold at a controlled velocity. So that linear velocity of the screw moving forward is used to control this process by controlling that velocity. Polymer melts are non-Newtonian in nature. So the faster it is forced into that smaller channel in the nozzle, the more shear it will want to go. The higher the shear, the less viscous the plastic will be and the easier it will be to flow. This can be both a beneficial to your process if you need it to get into small recesses and nooks and crannies within your cavity, but it can also be an issue if you start having problems with flash, when plastic is getting through the parting line and out into areas you don't want the plastic to be. Step 3 is pack and hold. So the screw holds a high pressure on the melt to ensure a complete filling of the mold as the melt cools in the final shape in terms of the pack. And then during the hold, the screw is just holding a lower pressure to make sure that no plastic is trying to come back out of the mold and back into the screw, just making sure that the volume stays the same as the part begins to cool. At this point, you filled the mold like 95% of the way before you start your pack. That pack, you're increasing the pressure to force the plastic into every single nook and cranny within your mold. After the entire mold is filled, you're just forcing even more plastic in there to ensure that your part remains the same shape that you want it to be. It's dimensionally stable, and to imbue a significant amount of strength to the part. Without that phase, you have a much weaker, much less consistent part. Step 4 is cooling and plasticizing. So basically the injection unit that you're seeing there, the screw starts reciprocating as the plastic, your plastic part in the mold sits there. And as the plastic part in the mold is sitting there, it's getting all that heat energy pulled out of it by the steel. The steel, usually there's cooling channels, maybe it's water or oil, to pull that heat out of there and maintain a certain steel temperature that you want to make sure that your cooling process stays the same, shot after shot, run after run, production lot after production lot. And finally, there's ejection. The mold is going to open, the part pulls and stays on the B side of the mold, and ejector pins come forward to push the part off the mold. So what are the benefits of designing a part for injection molding? Why would you go with injection molding? Well, first and foremost, really high outputs. As I said before, it's just a single step process in which an entire part is formed all at once. By adjusting for cavitation, wall thickness, which we'll get into, you can start to hit really high throughputs. Here at East Providence, one of our tools is has 16 cavities. That means for every shot, you are making 16 parts in 12 seconds. So every 12 seconds, 16 parts come out of the tool. That's 115,000 parts a day, 576,000 parts per business week. That's really good. In terms of cost effectiveness, we get these high outputs. We have inherent lightweighting. We'll get into this, due to how you should be designing your plastic parts, but also because of the material. Most polymers are lighter and less dense than metals or other comparable types of raw materials you might use for parts. And these are lower cost per pound and commercially available. Disregarding fire-resorbable medical resins right there. The wide range of materials includes tensile strengths going from anywhere from like 800 megapascals to 30,000 megapascals, going from elastomers to polyether imides, materials like that. You can easily introduce your unique additive. We take a lot of resins in and send them out to a compounding house where they take a neat base plastic material and compound in something like barium sulfate, for instance. And that makes the plastic part that we're making out of that material visible on X-rays or other medical imaging. So processes, there are glass fibers, which increase strength, pigments and colorants to make sure that you have the exact color that you might want your plastic part to have, and so on and so forth. Bioresorbable materials are a really interesting part right here. These are materials that can actually be implanted into the body and then dissolve over time. So if you get a surgery and you need staples or stitches or something, you actually don't have to go in for a second surgery to remove those staples. They just dissolve into like lactic acid or something that your body is very used to and very good at dealing with. So moving on, let's take a look at my example part here. It really speaks for itself. It's not well designed for basically any manufacturing process. As you can see, there's snap lock mate, there's undercuts, that weird through hole, all that stuff. So can we mold it? When we're talking about molding something, we need to understand ejection. That's where you'll see one half of the mold remains stationary That's the one closer to the injection unit, and the other half of the mold retracts and then forces the part off it. The mold that's retracting, the mold half that is retracting is the B side. That's the one with the ejector pins in it to retain and then force the plastic part off of. So this means that your part has to be able to release from one side and be retained on the other. You need to be able to split along a continuous parting line to properly mold whatever you need to mold. So in terms of our part, can we split this in two directions? As it is in that original view, no, we cannot. There are certain techniques you can use, like core pins, cams, wobble cores, expanding cores, dovetail, things that can get around this sometimes if you have like a through hole through the center of your part or something, or a threaded component that needs to be unthreaded. These can be dealt with. In terms of that snap fit, there's no good way to get the steel that's going to have to be there, because plastic isn't, we don't want plastic there. We need to get that steel out of there, and there's no good way to do that. So we're going to make some assumptions. One, the thing that matters about that strange through hole is that the orifice sizes those are critical, but maybe the path isn't. And then for the snap lock, we're going to say that the cantilevered like snap lock is going to be pulling in the direction indicated by the dark green arrow. So really that's the only service we need. We're just going to blow out that top section and create basically a pass-through core right there that where the steel can just pass right in there and easily form that geometry. So from here, now we've allowed our part to actually part from the mold. We're going to be looking at wall thickness. So wall thickness is more or less coring out your part. You want to get rid of big chunky areas of your part, because big chunky areas of your part are going to cool much less reliably than the thinner sections, and much slower, because of how much plastic likes to retain heat really during the molding process. You know, there's a reason it's an insulator and you're putting it in a heat conductive steel frame, or mold rather. And so when the part cools, it has to shrink. Plastic has a much greater rate of shrinkage than metal does. And so when a part is cooling, it's shrinking, and this causes sinks. If the skin of the part cools slower, basically the center of the part is going to shrink in and pull the skin of the part inwards, causing these divots in the part. Or worse, there's kind of an invisible defect called voids, where the skin might flash freeze more or less, and then the material will shrink towards the outside of the part and leave just pockets of nothing within your part that you can only really see if you cut it open or if you have clear parts. So apart from that, going for a low wall thickness will also, of course, affect your production rate, because the cooling times and how quickly your part's going to be capable of cooling, and material consumption, because I mean there's just less volume of material required to make one part. So when we get into wall thickness, this is a program called Mold Flow I used to make these two figures. What we look on the left is time to reach ejection. This is how long it will take that plastic to reach a suitable temperature for cooling. So what you're seeing there in red those are really big, thick, chunky parts that we need to get rid of. We need to find a way around that and remove a lot of material from those areas. And you can see on the right, the quality prediction is predicting those are going to be a lower quality than the rest of the part. That's due to what I was talking about before, those voids in those sinks. So it's correctly identifying what we already have. And so why does wall thickness matter, right? Basically, it controls a large array of the properties of your part. In terms of cooling time, that long equation right there, if you do it in scientific units, in metric, you can take the everything except the highlighted h squared will more or less reduce to 1. And if you take that h squared, h denoting your wall thickness in millimeters, if you, let's say it's a 2 millimeter thick part, you just square that, you have 4 seconds more or less of cooling time. That's your good rule of thumb, because all the rest of that equation boils down to more or less a coefficient of 1. So it looks really intimidating, but it's not, like a lot of things, right? Then we move on to wall thickness, which affects the moment of inertia. This is the stiffness of your part. We should pretty much be familiar with that. As the wall thickness increases, the stiffness of your part is going to increase. As it decreases, the opposite occurs. And then the wall thickness affects the pressure drop as well. So this is how much pressure it's going to take to fill your entire mold up, or fill your molded part. And you can see that, you know, there are a lot of benefits to reducing wall thickness. This is one of those things that you probably want to take a pause at, because as you reduce that wall thickness, your pressure drop is going to increase. It's going to take much more pressure to fill and pack out your part. And this can really affect what press you're going to have to start thinking about. Oh, is the injection molder I'm using capable of hitting these pressures? Are we actually going to be able to fill this part from these gating locations? That kind of thing. So here we've identified those red areas, and I've just cored them out. Coring out, I've just taken out that material all the way around the part and tried to shoot for about a 4 millimeter wall thickness all around. This is difficult because of that through hole and some issues with where that through hole's 4 millimeters of wall thickness meet with our snap fits 4 millimeters wall thickness, but you do the best that you can. So now one of the things you're going to be noticing is now that we've pulled out all that material, that looks a lot weaker in the center, and we might want to add something to remedy that. So we add reinforcement ribs. On the right, you'll see another graphic made by Moldful. That's a simulation we can run in-house for you if you don't have that capabilities. One of the other things you should be looking at, not just like structural integrity of your part in terms of the reinforcement ribs, but also where does the melt front meet? That's going to cause weld lines. Those can be like localized weakness areas. And that's also a place you may want to target where you're going to add your reinforcements. Because as the plastic, let's say the 2 melt fronts meet each other and move through a rib, that causes much better adhesion between the plastic and can really remedy that kind of issue. So here we see I've run the cooling time analysis again in Moldflow, and we've seen that there's actually another red area right, well, where it's red. And so that's another thick area. So we've done our best to core that out a little more and add reinforcement ribs that can reinforce, of course, and increase the strength of our part here. So there are some things you need to consider as you're adding reinforcement ribs. What's your thickness, your height of the reinforcement ribs, because you don't necessarily want them to be the same as your wall thickness. Here's why. So support ribs, the rule of thumb here is a thickness of 3/4 of your wall thickness and a height of 5 times your wall thickness. And you can see here that higher rib thicknesses cause localized thick sections like below, and those cause the sink defect that we've seen before, where those localized thick areas where the ribs are meeting your walls, those are going to cool at a different rate because you just have more heat in that area, more mass in that area to pull out of there. And that is going to result in these kind of aesthetic blemishes that might not affect functionality, but don't look so great if you're using a aesthetic surface. So let's take a look at these. You can see along the back end of this part where we have these thick ribs meeting the wall that there are little indents, especially at the base. It's difficult because anywhere you don't see plastic, there necessarily has to be steel. And any long areas where you're going to have steel, that steel, especially at its tips, are going to heat up and retain heat much better because they are further from the cooling channels, the water that is coursing through the mold and pulling that heat out of there into a temperature controller. And so larger ribs, even though they increase the strength and rigidity parts, they can really affect the aesthetic of the opposite surface. Now, you can kind of finesse these aesthetic issues by adding like a nice texture to that surface, a rougher texture, or some kind of like acid etched, I don't know, like snake skin or something like that, if you want to get kind of silly, right? But those can be used really well to cover up these kind of blemishes. Now, sometimes, I say in the final bullet point, sometimes remedies can be found during processing. Maybe you pack it out a lot more, and because of those much higher pressures, you are still forcing plastic into those areas as it shrinks and cools away and maintaining your aesthetic surfaces. However, if you have these issues and you catch them further along down the road, the old adage is for every step of the engineering process, catching a minor bug increase in cost by like 10 times. So let's say you find a remedy during processing where you have to pack that out. Well, you might start flashing a little bit. And all of a sudden you have a secondary process where you have to take parts and deflash them so that you don't get this aesthetic blemish. I mean, that just increased cost tenfold instead of a minor change to the design that an engineer can do in 20 minutes. Now, let's take stock here. In terms of material volume, we've reduced the volume of the part by 44%, which is a 44% decrease in cost. Fantastic. In terms of cycle time, we've gone from 10 minutes to about a minute of cycle time for cooling. So right there, a 90% reduction in machine rate cost. I used a machine rate of like $60 an hour because that's just much easier to work. really, really digestible number when you're talking about hours. The other benefit here is you're producing like 10 times as many parts as you would have been producing, increasing throughputs and scaling your process much better than you previously could. Now we're going to move into draft and ejection. So as I've said before in review, as the mold opens, the part needs to stick to the B side that's moving and has all your ejector pins in it and release from the A side. This is accomplished through the application of draft. Draft is basically an angle applied to the part walls, you'll see, that allows the part to release more easily from your mold when you have to eject it. So what's happening is as the part is cooling, the plastic shrinks. We've talked about that in terms of sink, but overall your part is shrinking around steel. The example I have here is more or less a core for like a cup or something. So if we have these hard 90-degree angles and it is straight up and down, that shrinkage is going to be, of course, directly normal to the steel, which causes the friction to directly oppose the ejector force, the ejector in green. So when the ejector system attempts to force the part out, it's working against that friction. This causes stress on the part and can result in deformation. The other thing about that is that the friction is working against the ejector system the entire time the part is being pushed off from that core. Now, if you add 1 to 2 degrees of draft, the part basically is, if it's moving upwards, the part will disengage from that core and easily come off it as soon as you break the gap, as soon as you move it up just a little bit. And so just by adding 1 to 2 degrees of draft, you've reduced the ability of your part to do damage to the mold, which I've seen, where ejector pins can actually be bent because a part is so trapped within that steel, it can actually just destroy and turn into springs these smaller ejector pins. And so when it comes to drafting your part, you're, like I said, looking for about 1 to 2 degrees. The nice thing about that 1 to 2 degrees is that's not really going to affect the functionality of your part. Usually, each part is kind of a snowflake. Each has a different function. That's something that you want to take on a case-by-case basis. But draft is incredibly important to the injection molding process, and that's why you should be accounting for it as you're designing and deciding what you really need out of your part. On the right, that's just draft analysis in SolidWorks, just to show that this is drafted by about 1 or 2 degrees on either side. We see that all the faces are correct and capable of pulling in the correct direction based on this draft analysis. The other thing is the direction of draft, which way the part is angled to draw down, is going to affect which side of the mold your part is going to, which side of the mold the features of this part are actually going to be molded on. So in the positive direction, maybe you're having all that on the A side. You probably want your core and snap fit on the B side, so that it as the part shrinks around it, the part is actually being dragged off and onto the B side and not being allowed to stay on the A side. That's just something to think about. Moving on, we have another little design rule of thumb, is adding fillets. So I thought I would take it kind of from a bird's eye manufacturing standpoint of just the basics of manufacturing the steel for your cavities. So your cavities are basically a negative of whatever plastic part you're trying to make. And to make those cavities, you're going to be using a variety of different processes that the mold makers have at their disposal. For very complex and intricate cavities, you're going to be using probably EDM burning. So EDM is a charged electrode, and probably many of the people on this call are familiar with this. But you're using a charged electrode shaped in the negative of the cavity to arc and burn steel off. Due to the rays arcing, your electrode can usually manufacture radii down to 2 to 1.5 thousandths of an inch. And so what's happening, and why a 90-degree on an electrode might not result in will not necessarily result in 90 degrees burned out of the cavity, is not just the rays of arcing, but as soon as you send current through that electrode, you are degrading it. So any 90-degree corners slowly become 1,000th radius corners and 2,000th radius corners. So to get down to a 2,000th, 1.5 thousandth radius, you're actually looking at manufacturing 2 to 4 electrodes based on how much burning you're going to need to get done. Theoretically, you can increase that to a much sharper corner. Theoretically, you can approach 90 degrees, a full 90 degrees, but you kind of start hitting this asymptote where of diminishing returns. And every time that you put electrode in, you are only burning a little bit, using it once and then pulling it out. And so it becomes cost prohibitive relatively quickly after the 2,000th to 1.5 point. All right, so a wire EDM is basically the same thing, but it's more for through holes where you have a full wire that also is sending current through it and arcing and burning off the steel. That can go down to a radius of about 2.5 thousandths based on the diameter of that wire. That's all going to determine on it. There are smaller radii for wire and larger radii for wire. I defer to the tool room, the mold makers, on what to use for sure. So these fillets are also important when it comes down to the plastic filling of the mold. When the melt front proceeds through mold, it flows around radius corners more repeatably and easily than sharp corners, for one thing. And then after molding, let's say you have a 90 degree corner, the plastic isn't necessarily going to completely fill that and make a true 90. As the plastic shrinks at the tip of that corner, it's likely that the plastic is going to cool at a slower rate and kind of deform into a slightly radiused corner as it shrinks away from the walls. Again, this can be remedied by increased packing, that kind of thing. But those are also stress concentrators within the plastic itself. The other area that's going to be helped by raising corners is cooling. Gradual radii present much better cooling properties for plastic. It makes the distance between the plastic and the cooling channels in the steel more uniform throughout the mold, and that provides more uniform shrink. So if you're not cooling repeatedly and uniformly through your entire part, you're going to be shrinking at different rates if you're cooling at different rates. And if you shrink at different rates on your part, you're going to see warping and deformations out of the mold. You know, a perfectly flat piece, or what should be a perfectly flat piece in steel, you could see it come out of the mold and warp into a potato chip kind of shape or something like that. Also, in terms of fillets, or at least rounding of corners, one of the things you want to look at is radiusing all the corners on your walls. If you're making some kind of box or something like that, and you have 90-degree corners, you want to be thinking about radiusing them down and maintaining that uniform wall thickness throughout your entire part. The rule of thumb here is more or less an inner radius of half of your wall thickness, and the outer radius being equivalent to your inner radius plus your wall thickness, or 1.5 times your wall thickness. And that just ensures that wall thickness remains the same around the corner, cooling will be even more even, and it just allows for a better strength and less stress in your part. So in terms of fillets, as we discussed, it's much easier to produce filleted corners than it is to make 90-degree corners. It's nice to be about 10 thousandths to 2 thousandths if possible. Minimums being around 2 thousandths to 5 thousandths. Usually, we've certainly seen lower, and we've been capable of achieving lower. But in terms of ease of manufacturability, that might be what you want to target. Another thing is, a lot of part drawings will show 90-degree corners, and you can say in the notes maximum fillets or radiuses on part corners where permissible, and spec out, say, a maximum of 3 thousandth or 5 thousandth fillet right there. So one of the other things fillets, especially around ribs, are going to do is it's going to increase the localized thick sections around those ribs, as we talked about, and exacerbate those sinks that you see. That's something you really need to take into account when you're thinking about, oh, well, how much can I fillet these areas versus these other ones? Can I fillet where my ribs meet my wall if the opposite is an aesthetic surface? And should I be redesigning my ribs to a lower thickness then to compensate for that? And so it's certainly something to consider as you're moving through the design phase. And now, like I said before, every part is a snowflake. They're all unique. All these functions are unique, so not every corner can necessarily be filleted, and we understand that, and we often work with customers on that. There are techniques we can use in terms of how the mold is actually constructed to make those 90-degree corners and really make the part that needs to be made, right? There are also areas like along a parting line where the steel is meeting steel that can't be filleted or shouldn't be filleted. And so that's something that we'll go over. We often go with the customer and talk through that. And that's something that should definitely be considered as you are moving through the design phase and looking for a DFM analysis and that kind of thing. And so let's take a look. What's our final part look like? All right, this little guy should have started. Wonderful. All right, so overall, the coring out saved us 85% in cost due to machine rate and material savings. Opening one side of the snap fit allows the part to actually be molded. The ribs are maintaining strength and aiding in the processing of the material. And the addition of draft allows the part to actually be ejected. Finally, radius and corners are mitigating the stresses and aiding cooling, and the filleting of all those areas allows the steel to be manufactured in the corners to actually be to spec. So now I get to talk about my site, MW Components East Providence. So in my time here, I've worked on a wide range of projects, a lot of different use cases, a lot of different industries. We've gone industrial, automotive, medical, just a whole range of things. We do overmolded parts, we do micro parts, we've done threaded parts, optical parts as well. And so what you'll see in that small picture next to the dime head are micromold parts. Those are envelopes of less than 1/4 of an inch to square, more or less. That definition can vary. We have unthreading parts, and you see at the bottom right, overmolding on various different inserts, reel to reel, on strips, that kind of thing, and an expertise with a really wide variety of materials. Usually a customer will come to us with their material spec'd out, but recently, as of late, we've been getting a lot of requests for general purpose nylons, general purpose ABSs. We can kind of go out with that. But of course, there's a wide variety of materials that we've personally had experience with here, with bioresorbables, engineering resins like polyimides, Ultem, PEEK, LCP, polyphenylene sulfone, consumer and industrial grade resins like ABS, PMMA, polypropylene, polycarbonate, and we've done a good amount of elastomers as well. And so throughout those, we should be able to, we probably have run whichever material you might be considering. We probably have experience with it, and we probably have someone here on the floor who has held it in their hands at some point. The same thing with any additive materials you might be trying to have in your part to adjust your strength and the properties of whatever part you're trying to create. Finally, we have really close relationships with mold makers who help us through the design phase, and tooling up is one of the terms of phrase for actually building a mold and going from a concept to production phase. We work a lot with domestic mold makers and have been able to source internationally with success as well. And so if you ever want to go over our general catalog, you can visit that link right there, moldcomponents.com, or under manufacturing services in the injection molding section, and you can check that for details. So I guess we can move into the question and answer phase.
All right, thank you, Will. We're now going to start our Q&A. As a reminder, if you have questions, please enter those in the Q&A section available at the bottom of your screen now, and I'll read them aloud for everyone to learn from our presenters' responses. I'd also like to note that if you have questions of a proprietary nature, you can send an email to our presenter, Will, and he'll be happy to answer those questions privately. Will's contact information is shown on your screen now, so you can record that down, take a screenshot, or send him an email now or later, and he would be happy to hear from you. We do have a couple of questions, so we're going to go ahead and get to those. The first one is, how do you decide where the parting line should be when designing a product?
That's a really good question. And that depends a lot on the part geometry. We've dealt with many parts with strange geometries that you're going to want existing on either the A and B side of the tool. So when we get into that, the B side is the part you want is the side of the mold you want your part to stick to. So we try and get a lot of the cores, deep coring on that side, so that the parts shrink around those and actually get that friction and get pulled to one side. That's something to think about when you're dealing with parting line. The other thing to think about during parting line is that a parting line is where you're going to have where your steel meets the other steel. That's where you can start to see defects like flash. And that's the most easily damaged area of your mold. So you want to, if you have the ability to, you also want to think about where on my part, I know no one wants to say or think this, but where on my part can I have small blemishes or defects? And that would be a good place to start. You don't want your parting line across a critical surface. It leaves a witness line. You don't want it across an aesthetic surface necessarily. But if you have to have it there, you can. There are, of course, workarounds for all these.
Okay, perfect. A few more. What type of mold tooling is used to create threaded parts, or is a threaded part, or is it threaded post mold?
Okay, yeah, no, this is actually really interesting. So there are a lot of ways to thread your parts. And what we do mostly in here is in mold threading. And so that is the part is actually formed with those threads. And before the mold opens, those threads are unscrewed. You actually have screws that unscrew from your parts and create those threads in one single step and fall out. We have one running that I can see now from where I'm sitting, uh, where a giant piston is basically rolling a screw out of the mold and unscrewing it. Although, to your point, that kind of complex geometry for your mold, that's going to obviously incur a higher cost for your tool, a higher upfront cost. So it is possible to basically just make that a tapped diameter and go in there and tap it afterwards. We've had secondary processes like that, but just know that there's diminishing returns, and it might be worth your while to think about paying the upfront cost for the tool to do that for you.
Okay, we had a very specific question here, and I hope I'm saying this correctly. How do you test the impact strength of products with PC and acetyl copolymer?
Oh, acetal, polycarbonate acetal. This is so yeah. This was actually when I taught grad labs. The impact testing was usually going on right next to me. There were constantly shards of polycarbonate or acrylics flying across the lab. Usually, if you look at a material data sheet, you will see the impact strength. That is an ISO test or an ASTM testing standard. You're going to want to produce pucks. A lot of testing labs can do this for you. If you have a material, you want to get pucks, and it's like a drop dart test where you bring a steel dart of a certain tip radius to a certain height, implying a certain potential energy. And that potential energy, of course, becomes kinetic energy as it hits the part, and then you look at the part for blemishes or cracking. That being said, when it comes to the actual functionality of your part in particular, you might want to develop your own impact strength. I know with hard hats, you do a similar thing where you produce the whole hard hat, you put it under a steel tipped dart, and you bring the dart up to a certain height, and you drop it down, and you calculate the energy at which it did or did not break from there.
Awesome. This next one I think is a very good question. Do you have a list of parts already injected molded that could be purchased without having to make a new custom mold?
Yes, we have a smaller list of those. When it comes down to our business model, usually we're dealing with more custom injection molded parts, where customers come to us with their specific drawings. However, I believe there are strainer leaf boots that we make here that are just general use, and we can accept orders on those.
Is it possible to modify an existing design and possibly save costs?
Yeah. One of the things we do here, if we have a customer that needs to tool up very quickly and get shots off a mold, and they have simple geometries, we have a tool room in-house that can basically, I don't want to say cannibalize, but we've been around for 40 years, and we have molds in the back that are from defunct customers that no longer exist, that we own the tools from. And so we will usually take the cavity blocks out of those and be able to repurpose the overall frame, but make new cavity blocks for a customer coming in. And that saves on time and cost.
Lovely. We had a question about draft angles. They were asking you to address draft angles and if they vary by material.
Yes. No, that's a fantastic question. I know. So draft angles, of course, are going to rely on a number of things. When it comes down to difference in draft angles for materials, what you're going to want to look at is how much does the material shrink, for one. There might be a recommended draft angle at a certain surface texture or roughness, but really what's going to affect your draft angle is how rough your surface is. So you want to spec out, let's say you're going with like a B or C class, class C or class B finish. That might imply a higher draft angle than a class A, like mirror finish. Or if you're going with an acid wash texture, you might be wanting to go with a much higher draft angle to clearly pull that texture off your part. But when it comes down to types of material, really what's going to affect it is more the surface roughness and not so much the material itself. But again, the material, if there is a spec'd out draft angle for that material, it should be found on the technical data sheet of the plastic from whatever resin supplier usually makes that. That's something I'm remembering. I think I have seen on certain technical data sheets before, but it's not necessarily the greatest compounding factor here.
Okay, we had a follow-up question to our first question that we had in the queue about the parting line, and someone asked where the parting line would be in the example part that you showed. And so you sort of went over that on slide 7. I don't know if you want to navigate back to that.
Well, actually, so on this draft analysis, you'll see where the red meets the green, that's really your parting line. So on the outside, I have everything in red being on one half of the steel, and where it hits the green, that's your parting line. And you can see here that I have this entire section made out of a single piece of steel that's coming from the bottom of the part and going up to here. And then all of this is being created and formed by steel on this side. So the parting line is actually internally somewhere down here in this section. The parting line is up here for this core. And then on the outside of the part, your parting line is right here. Continues.
Awesome. What do you do in the design phase to combat shrinkage of plastics?
Right. So again, I'm going to go back to the technical data sheet. Once we're really serious with the customer, we start designing the product for the mold. We're going to start looking at the specific resin we want to use. At this point, the resin's usually been spec'd out, and we've landed on one specific grade of resin. And so that specific grade from whichever material supplier will have a technical data sheet, as I mentioned during the draft angle question. And that technical data sheet has the percentage shrinkage, usually around 0.5 to 1% shrinkage around there. It can be greater or less, depending on whether or not you're on a number of factors to deal with the chemistry of your plastic. But you can take that number, let's say 1% shrinkage, and actually just more or less scale up your model. Of course, when you're talking about that, if you have glass fibers, fiber orientation is also something that would need to be taken into account, because fibers in the flow direction will shrink differently than fibers across the flow direction, because they're going to be pointing a single way repeatedly. And so the area between the fibers, if they point one way, the area between the fibers is going to shrink more than the area in which the fibers are pointing. I wish I had it'd be easier to explain with like an image or something, but I hope you understand my meaning there. But that's something that we deal with every day, and is something that we can accurately predict, especially when we begin to discuss with the tool makers and mold makers.
Okay. While we were answering that question, another question came through about parting line. So I'm glad you're still on this example. Maybe you can show it with this. Can the parting line be at the edge of a part, or does there need to be material on both sides?
Yes, it can be on the edge of a part, just along the edge of the part, if I understand this correctly. So like on the outside, you can have a full parting line where, the only issue is there's this under bit right here. But if this whole thing could all be on one side of the part, you could just make it all on a single side of your part, except for, and if you blew out I believe there's walls in these, or ribs in these cavities right here. If you took all that out and were able to have steel coming up all the way to here, then only this face would really have to exist on the A side of your mold, and everything else could exist on the B side of your mold. So it is possible. It just depends on your part complexity and your specific part's geometry.
Okay. How do different surface textures affect draft? And is there a calculation that you can do for surface roughness to anticipate that draft?
Yeah, I don't have the calculation on hand right now, but there is a general calculation you can do relating the surface roughness to, let's see if I can find it. There's a calculation you can do where you take that surface roughness, and I believe you can look up a coefficient of friction related to that, and that would determine your friction factor right there. Taking that friction force, by calculating that friction force, you can then calculate the angle you would need to make. You would then be able to back calculate your draft angle from a calculation in which you set your ejector strength equal to or greater than, probably greater than your friction strength to a factor of like 2 or 3 from there. But yes, rougher textures, etched textures will all really affect what draft angle you require. Etched textures like what I talked about, the snake skin are kind of really boutique textures. Those ones are a lot rougher, and they're there for an aesthetic reason, usually, like a faux leather or something. And you're going to want a higher draft, not so much because you need to ensure that your part can eject and overcome that friction from the shrinkage, but also because you want that to release cleanly, and so that you can clearly see that texture. It doesn't start smearing or getting stuck in crevices and stuff like that. So that's a good question.
Someone asked, I'm looking to reduce costs and weight and was wondering if there are plastic materials I could use to potentially replace some of my glass components. Is that possible? And is that something that MW Components has experience doing?
Yeah, so when it comes to glass, of course, everything comes down to what's the function of the part, what's the functionality. One of my first projects here was actually for a part for a research lab, where they were making glass components. They're about a 1 inch cubed glass light guide, which was directing light toward a small little diode or something right at the tip, or from a diode into scintillating fibers at the base, I think. And so that little part was made out of glass. It cost like $100 to make. It took like an hour to make one of them because it's a subtractive process. So they kind of have to cut away the glass and make sure it has a certain surface finish. And we were actually able to find an acrylic, or they were able to find a PMMA, a polymethyl methacrylate resin with a very similar refractive index. And we were then able to take that and mold it into the same shape for a tenth of the cost. And of course, significantly less weight and much higher throughputs for them. So yeah, that is something we're capable of. We've also done micro optics in the past. So we have ongoing micro optics projects as well. So it's certainly something that's viable.
Can I get pre-made mold blocks and do my own machine work?
Cavity blocks, yes. We've done projects kind of like that in the past, where we have tooled up into a frame and then have had mold blocks made in the general shape of the part, and then set those back to the customer and have the customer machine out to their specification exactly what they wanted in the steel, and then we were able to take that and mold it. If you're looking to do that, not in the context of a contract molder, you could go to a machine shop and as long as you're going there with a certain frame size, you can get something called a mud frame, a universal frame. You would just go to a machine shop and say, I need 2 pieces of steel with water lines cut through them with this kind of area untouched where I can actually make my part.
Okay. Is there anything I can do to make my plastic parts greener or recyclable?
Yeah, actually, this was something of a pet project at UMass Lowell when I was there for my my undergraduate, my master's. I took a lot of classes. They offered a lot of classes in making plastics more green, and it's something certainly that's on my mind as a plastics engineer, since there's been a lot of rather difficult, rather bad press from plastics and microplastics. You kind of have to look at your life cycle in a very holistic way of your part. From cradle to grave was the saying that was beaten into me at university, right? And so at the cradle, you're talking, what material am I going to use? Is the material I'm using renewable? Is it made from renewable sources? The great thing about plastic and most polymers that we use for plastic injection molding, it's more or less 90% carbons, hydrogens, and oxygens. Carbons, hydrogens, and oxygens are like 3 of the most readily available, elements out there. And so you can take a lot of feedstocks, process them down to their basic elements, and then put them in the right order to make a lot of different plastics. And so thinking about that is good. And then on the other side, how when my part is broken and no longer of use, when it's phased out, what happens to it? One of the things that is good to think about is, is my part biodegradable? There are more and more ways you can attain that. Currently, one of the best resins for that is polylactic acid, but PLA polylactic acid is just lactic acid like your body makes turned into a long chain form, and that is capable of, just like your body breaks that down and processes every day, you can compost that, and that can break down into its constituent particles better and not create microplastics, but actually drop down to its basic carbons, hydrogens, and CO2 and that kind of thing. The other thing is recyclability. Can my part, how easy is it for my part to get processed in a recycling plant or something? And that really comes down to, can I make my part out of a single material? Does it have to be an assembly with metal screws in it, which are really difficult to get out and can really confound and stop the recycling process? There are ways around that: snap fits, press fits, things we design around very often. And then that kind of thing, really. It doesn't have to be an assembly, or can this entire assembly just be made out of the same polymer or material?
Okay, so for the interest of time, we're going to go ahead and conclude Q&A. There are a couple more questions in the queue. We're going to follow up with those through email. We'll go ahead and navigate to slide 27 for me, please. All right, so if you think of additional questions after the call, please reach out to our presenter, Will Johnson, at wjohnson@mwcomponents.com, and he'll be happy to answer more questions.
Sorry. I'm one of the strange ones because I'm with EVP. I'm William Johnson.
Oh, yes. Thank you. Thank you so much.
Makes me different than everyone else here.
I'd like to thank our presenter and all of you for joining us. We'll be following up through email with a link to the recording so that you can share it with your peers or use it for reference later. As a reminder, MW Components manufactures stock and custom parts, including springs, fasteners, bellows, couplings, and other precision metal and plastic components. We accelerate the entire process of delivering stock and standard parts to almost any volume or tolerance and against demanding deadlines, as well as custom parts. With MW Components, you can be sure you'll get the right part to the right specification each and every time. For more information on MW Components products, services, and available resources, including white papers, case studies, and webinars, please visit mwcomponents.com/resources. This now concludes our webinar. Thank you all for listening and have a great day.